In the vast expanse of our solar system lies Mercury, the first sentinel from the Sun, a sweltering, rocky world that holds clues to the formation of our planetary system. Its surface, scarred by cosmic bombardment, whispers tales of a turbulent past, while its eccentric orbit and unusual rotation hint at powerful gravitational forces. Despite its diminutive size, Mercury is a world of extremes, with scorching daytime temperatures and frigid nights. Its desolate landscape of craters, plains, and towering cliffs bears witness to relentless asteroid and comet impacts. Over the centuries, astronomers have pieced together a picture of Mercury using Earth-based telescopes and spacecraft missions. Each new observation brings us closer to understanding this mysterious world. Yet Mercury continues to surprise and challenge our assumptions. Mercury's small size belies its importance in our understanding of planetary formation and evolution. Its heavily cratered surface, reminiscent of our moon, suggests it has been geologically inactive for a very long time. Recent observations have revealed tantalizing hints of water ice hidden within permanently shadowed craters at Mercury's poles. This discovery raises intriguing questions about the potential for volatiles, including water, to exist on other airless bodies in the inner solar system. Instead of a substantial atmosphere, Mercury possesses a thin exosphere, constantly replenished by solar wind particles and gases released from the planet's surface. Despite its many mysteries, Mercury is a captivating world, a testament to the diversity and wonder of our solar system. As we continue to study Mercury, we gain a deeper appreciation for the complex processes that have shaped our planetary neighborhood. Mercury's orbit around the Sun is a marvel of celestial mechanics, a testament to the intricate dance of gravity that governs our solar system. Unlike the nearly circular orbits of most planets, Mercury's path around the Sun is highly elliptical. This eccentric orbit takes Mercury on a wild ride, swinging it close to the Sun at perihelion and flinging it far out into space at aphelion. As Mercury races towards perihelion, its speed increases dramatically, causing surface temperatures to soar. Conversely, as Mercury swings out towards aphelion, its speed slows and temperatures plummet. In addition to its eccentric orbit, Mercury has an unusual rotation pattern known as a 3-to-2 spin-orbit resonance. This unique resonance has a profound effect on the length of a day on Mercury, making it longer than a Mercurian year. Despite its close proximity to Earth, Mercury has long remained one of the most mysterious planets in our solar system. The first spacecraft to visit Mercury was NASA's Mariner 10, which made 3 flybys in the 1970s. Mariner 10's images revolutionized our understanding of Mercury, revealing a heavily cratered surface, a tenuous atmosphere, and a global magnetic field. In 2011, NASA's Messenger spacecraft entered orbit around Mercury, mapping its entire surface in unprecedented detail. Messenger's data revealed a history far more dynamic than previously thought, with evidence of past volcanic activity and water ice in permanently shadowed craters. Future missions will build on the legacy of Mariner 10 and Messenger, delving deeper into Mercury's history, composition, and environment. Bathed in the relentless glare of the Sun, Mercury might appear to be a desolate and unchanging world. Its surface, a canvas of craters and ancient lava flows, speaks to a violent past. Mercury is classified as a terrestrial planet, meaning it's a rocky world like Earth. Its surface is composed primarily of silicate rocks and dust, similar to the lunar highlands. Scientists believe that Mercury's interior is dominated by a massive iron core, which makes up a staggering 70% of its total mass. One theory suggests that Mercury was once a much larger planet, perhaps twice its current size. Early in its history, this proto-Mercury may have experienced a catastrophic collision, stripping away much of its outer layers. Another theory proposes that Mercury formed in a region where the Sun's intense radiation vaporized lighter elements, leaving behind heavier elements like iron. Mercury's large iron core has profound implications for its overall structure and evolution. Mercury's surface is a testament to the extremes of its environment, shaped by the searing heat of the Sun and the frigid cold of its long nights. One of the most striking features of Mercury's surface is its abundance of impact craters, a silent reminder of the chaotic early history of our solar system. The density of craters on Mercury's surface suggests that it has been geologically inactive for a very long time. There's evidence of past volcanic activity, with vast plains of smooth, solidified lava flows covering many low-lying areas. Perhaps the most surprising discovery about Mercury's surface is the presence of water ice hidden within permanently shadowed craters at its poles. The ice is believed to have been delivered by comets and asteroids, accumulating in these cold, dark traps where it remains stable, even today. This discovery has profound implications for our understanding of the distribution of water in the early solar system. Deep beneath Mercury's cratered and sun-baked surface lies a mystery, a massive iron core that dominates the planet's interior. Mercury's core is estimated to make up around 70% of its total mass, a stark contrast to Earth. Several theories attempt to explain the formation of Mercury's oversized core. One possibility is that Mercury was once a much larger planet, perhaps twice its current size. Early in its history, this proto-Mercury may have experienced a giant impact, stripping away much of its outer layers. Another theory suggests that Mercury's core grew to its enormous size due to the intense heat of the early solar system. The composition and structure of Mercury's core have profound implications for the planet's overall evolution. The presence of a liquid outer core could explain Mercury's weak magnetic field, generated by the motion of electrically conductive fluids within its core. As if its scorching temperatures and unusual orbit weren't enough, Mercury also presents a curious geological puzzle. Its surface is shrinking. This phenomenon, evidenced by numerous lobate scarps or wrinkle ridges, provides a unique window into the ongoing geological activity deep within Mercury's interior. Lobate scarps are giant thrust faults formed as the planet's crust is compressed. They appear as long, arc-shaped cliffs extending for hundreds of kilometers. These scarps formed as Mercury's interior cooled and contracted over billions of years. The shrinkage of Mercury's surface is directly related to the cooling and solidification of its massive iron core. Despite its small size, Mercury harbors a weak but persistent magnetic field. This magnetic field plays a crucial role in shaping its atmosphere and protecting its surface from the solar wind. Generated by the dynamo effect, it suggests part of Mercury's core is still molten. Mercury's magnetic field, though weak, deflects most of the solar wind, creating a magnetosphere. However, its proximity to the sun means the solar wind can sometimes penetrate, affecting its surface and atmosphere. Studying Mercury's magnetic field offers insights into its internal structure and evolution. Deep within Mercury's sun-scorched exterior lies a massive iron core, proportionally larger than any other planet in our solar system. This iron heart holds clues to the processes that shaped Mercury and the inner solar system. Mercury's core occupies 70% of the planet's volume. This is in stark contrast to Earth. The reason for Mercury's large core is debated, with theories suggesting a cataclysmic collision or solar nebula condensation. The abundance of iron within Mercury's core is a tantalizing clue to the planet's formation. While iron is common, Mercury's concentration is unusually high. This has led scientists to explore Mercury's metallic heart. One theory suggests Mercury formed in an iron-rich region of the solar nebula. Nearby supernovae could have influenced this enrichment. Alternatively, the inner solar system's heat may have vaporized lighter elements, leaving behind a residue enriched in heavier elements like iron. Understanding Mercury's iron abundance helps us learn about planet formation. Mercury's early history suggests a molten sea of magma, a fiery crucible where its fate was forged. The magma ocean hypothesis proposes that Mercury's surface melted, forming a global ocean of molten rock. As it cooled, denser materials sank to form the core, while lighter materials formed the mantle and crust. This differentiation left a layered structure, supported by evidence from spacecraft missions. In the face of the sun's relentless radiation, a constant barrage of charged particles streaming outward at supersonic speeds, Mercury might seem like an unlikely candidate to possess a magnetic field. Yet, despite its small size and slow rotation, this enigmatic world harbors a weak but persistent magnetic field, a shield that deflects the worst of the solar wind and protects its tenuous atmosphere from being stripped away into space. Planetary magnetic fields are thought to be generated by a process known as the dynamo effect, a complex interplay between a planet's rotation, its electrically conductive core, and the convection currents that transport heat from the interior to the surface. Earth's magnetic field, for example, is generated by the churning of molten iron in its outer core, driven by the planet's rotation and the heat released by the decay of radioactive elements. Mercury's magnetic field, while significantly weaker than Earth's, is thought to be generated by a similar mechanism. Although Mercury's core is much smaller than Earth's, it is believed to be at least partially molten, allowing for the circulation of electrically conductive iron. The planet's slow rotation, while seemingly a hindrance to dynamo action, is offset by the strong tidal forces exerted by the Sun, which can also contribute to stirring the core and generating electric currents. The presence of a magnetic field on Mercury has profound implications for our understanding of the planet's interior and its evolution over time. The fact that Mercury still possesses a magnetic field, albeit a weak one, suggests that its core has not completely solidified, as might be expected for a planet of its size and age. This suggests that Mercury's core may contain a higher proportion of lighter elements like sulfur, which would lower its melting point and allow it to remain partially molten for a longer period. Furthermore, Mercury's magnetic field plays a crucial role in shaping its interaction with the solar wind. The magnetic field lines act as a barrier, deflecting most of the solar wind around the planet and creating a magnetosphere, a region of space dominated by Mercury's magnetic influence. This magnetosphere, while much smaller and weaker than Earth's, provides a degree of protection from the Sun's radiation, helping to preserve Mercury's tenuous atmosphere and shield its surface from the full brunt of the solar wind. While Mercury's orbital dance around the Sun is a marvel of celestial mechanics, its rotation on its axis is equally intriguing, revealing a unique and unexpected phenomenon known as a 3-to-2 spin-orbit resonance. This resonance, a consequence of the Sun's powerful gravitational influence on Mercury's elongated shape, dictates that for every 3 rotations on its axis, Mercury completes precisely 2 orbits around the Sun. This 3-to-2 resonance has a profound effect on the length of a day on Mercury, as measured from sunrise to sunrise. A single solar day on Mercury, the time it takes for the Sun to return to the same position in the sky, lasts for a staggering 176 Earth days, longer than a Mercurian year. This means that a single day on Mercury is twice as long as its year, a bizarre consequence of its unique spin-orbit resonance. The origin of Mercury's 3-to-2 spin-orbit resonance is thought to be linked to the planet's early history and the tidal forces exerted by the Sun's gravity. As Mercury formed and solidified, its molten interior responded to the Sun's gravitational pull, creating bulges that were aligned with the Sun's direction. Over time, these tidal bulges exerted a torque on Mercury, gradually slowing down its rotation until it became locked in its current 3-to-2 resonance. This resonance has profound implications for the planet's environment and surface conditions. One hemisphere of Mercury faces the Sun for a prolonged period during its slow rotation, experiencing scorching temperatures, while the other hemisphere faces the coldness of space. This extreme temperature difference creates a unique thermal environment on Mercury, unlike any other planet in our solar system. Mercury's highly eccentric orbit, the most extreme of any planet in our solar system, is a testament to the chaotic and often violent nature of planetary formation. While the precise cause of Mercury's unusual orbit remains a subject of scientific debate, it is thought to be the result of gravitational interactions with the other planets in the early solar system. As the planets formed from a swirling disk of gas and dust surrounding the young Sun, they interacted with each other gravitationally, pulling and tugging on each other's orbits. These interactions could have had a profound effect on the shapes and orientations of planetary orbits, sometimes leading to collisions, ejections, or in the case of Mercury, a highly eccentric orbit. One theory suggests that Mercury's orbit was perturbed by a close encounter with another planet, perhaps Venus, or even a now-vanished planet that once existed in the inner solar system. This gravitational encounter could have flung Mercury into its current eccentric orbit, leaving it on a wild ride around the Sun. Another theory proposes that Mercury's orbit is the result of a more gradual process, a slow migration inward towards the Sun, driven by gravitational interactions with the protoplanetary disk. As Mercury spiraled inward, its orbit became increasingly elongated, eventually settling into its current eccentric path. Whatever its cause, Mercury's eccentric orbit has had a profound effect on the planet's evolution and environment. The extreme temperature variations caused by its varying distance from the Sun have shaped its surface geology, influenced its atmospheric composition, and even affected its internal structure. From our vantage point on Earth, Mercury appears to move across the sky in a peculiar way, sometimes appearing to reverse its direction of motion in a phenomenon known as retrograde motion. This apparent backward dance, an illusion caused by the relative positions and speeds of Earth and Mercury in their orbits around the Sun, has fascinated and puzzled observers for centuries. Retrograde motion is a consequence of the fact that Earth and Mercury are both orbiting the Sun at different speeds and distances. As Earth overtakes Mercury in its orbit, Mercury appears to slow down and then move backwards in its path across the sky. This retrograde motion is not unique to Mercury. All the planets in our solar system exhibit retrograde motion at some point in their orbits as seen from Earth. In the case of Mercury, its retrograde motion is particularly noticeable because it is the closest planet to the Sun and therefore has the fastest orbital speed. Mercury's retrograde periods occur several times a year and typically last for a few weeks at a time. During these periods, Mercury appears to move westward across the sky, opposite to its usual eastward motion. Ancient astronomers were puzzled by the retrograde motion of planets, as it seemed to contradict the prevailing geocentric model of the universe, which placed Earth at the center of the cosmos. It wasn't until the development of the heliocentric model, which placed the Sun at the center of the solar system, that the phenomenon of retrograde motion could be explained as a simple consequence of the relative motions of Earth and the other planets. The gravitational dance between Mercury and the Sun is not limited to their orbital interactions. It also manifests in a more subtle but equally profound phenomenon: tidal forces. These forces, arising from the difference in gravitational pull across a planet's diameter, have played a crucial role in shaping Mercury's rotation, its internal structure, and even its surface geology. The Sun's gravitational pull is stronger on the side of Mercury that is closer to the Sun, and weaker on the side that is farther away. This difference in gravitational pull creates a tidal bulge on both sides of the planet, stretching it slightly along the line connecting Mercury to the Sun. As Mercury rotates on its axis, these tidal bulges are carried slightly ahead of the line connecting Mercury to the Sun due to the planet's inertia. This misalignment creates a torque, a twisting force, that acts on Mercury, gradually slowing down its rotation over time. This tidal braking effect is thought to be responsible for Mercury's unique 3-2 spin-orbit resonance. Over billions of years, the Sun's tidal forces have gradually slowed down Mercury's rotation, until it reached a point where its rotation period became synchronized with its orbital period in a 3-2 ratio. Tidal forces have also influenced Mercury's internal structure. The constant squeezing and stretching caused by tidal forces generate heat within the planet's interior, contributing to the maintenance of a partially molten core. This molten core, in turn, is thought to be responsible for generating Mercury's weak but persistent magnetic field. From our perspective on Earth, Mercury might seem small and insignificant, often lost in the Sun's glare. However, Mercury is a fascinating world with extreme environments and unique characteristics. Its proximity to the Sun makes it key to understanding planetary formation. Studying Mercury helps us learn about the early solar system and exoplanets. Its unique spin-orbit resonance and magnetic field offer insights into planetary dynamics. By studying Mercury, we refine our models of planetary evolution. Mercury's place in the solar system is crucial for understanding our universe. Across our solar system, celestial bodies bear scars of a tumultuous past, pockmarked by asteroids and comets. Mercury's ancient surface is adorned with craters, each a testament to cosmic collisions billions of years ago. Craters form when space objects slam into larger bodies, releasing immense energy and creating shockwaves. Mercury's surface is heavily cratered, more so than any other terrestrial planet. This abundance of craters reflects a violent history, especially during the late, heavy bombardment. During this epoch, the inner solar system was a chaotic shooting gallery of asteroids and comets. The largest impact basin on Mercury, Caloris Planitia, spans 1,550 kilometers. This colossal impact likely influenced Mercury's evolution, triggering volcanic activity. The impact craters that adorn Mercury's surface are not merely cosmetic blemishes. They are indelible records of the planet's violent past, each scar telling a story of cosmic collisions that reshaped its surface and influenced its evolution. Among the most striking features associated with these ancient impacts are the vast impact basins, sprawling depressions that testify to the immense power unleashed when celestial bodies collide. Caloris Planitia, Mercury's largest impact basin, stands as a testament to the immense power of these cosmic collisions. This colossal scar, spanning 1,550 kilometers and ringed by mountains that rise up to 2 kilometers above the surrounding plains, was formed by the impact of an object estimated to have been at least 100 kilometers across. The energy released upon impact would have been staggering, equivalent to millions of nuclear bombs detonating simultaneously. The shockwaves generated by the Caloris impact reverberated through Mercury's interior, triggering widespread volcanic activity and fracturing the planet's crust. On the opposite side of Mercury, antipodal to Caloris Planitia, lies a region of chaotic, jumbled terrain known as the Weird Terrain. This region is thought to have been formed when the seismic waves from the Caloris impact converged on the opposite side of the planet, focusing their energy and disrupting the surface. Impact basins like Caloris Planitia are not the only scars left behind by Mercury's violent past. The planet's surface is also crisscrossed by numerous lobate scarps or wrinkle ridges, long arc-shaped cliffs that can extend for hundreds of kilometers. These scarps are thought to have formed as Mercury's interior cooled and contracted over billions of years, causing its surface to buckle and fold. Despite Mercury's scorching surface, ice exists in permanently shadowed craters at its poles. These cold traps maintain temperatures far below the planet's average. Radar observations and NASA's Messenger confirmed the presence of water ice. This ice likely came from comets and asteroids impacting Mercury over billions of years. While impact craters dominate Mercury's surface, the planet's landscape is not solely defined by these scars. Beyond the craters lie vast plains and ancient volcanic features, revealing a dynamic world. Smooth plains cover much of its low-lying regions, formed by volcanic eruptions. These plains, similar to lunar Maria, were created by low-viscosity lava. Some plains date back to the early solar system, while others are more recent. Mercury's surface also shows evidence of explosive volcanic activity. Volcanic vents with pyroclastic deposits suggest eruptions of gas and ash. These deposits provide evidence of Mercury's once active interior. Impact cratering and volcanism have shaped Mercury's surface. The planet's atmosphere, bombarded by solar wind, contributes to space weathering. Micrometeoroid impacts also play a role in shaping the surface. In the vast emptiness of space, Mercury's exosphere is a tenuous whisper, a delicate balance between forces stripping it away and those replenishing it. Unlike Earth's thick atmosphere, Mercury's exosphere is so thin that atoms rarely collide, behaving like individual particles. This exosphere, almost a vacuum, shapes Mercury's surface and its interaction with the solar wind. Elements in Mercury's exosphere come from its surface, liberated by micrometeoroid impacts, solar wind sputtering, and thermal desorption. Mercury's proximity to the Sun, while a source of both wonder and peril, places it in a unique and challenging cosmic environment. Bathed in the Sun's intense radiation and constantly buffeted by the solar wind, a stream of charged particles emanating from the Sun's corona at supersonic speeds, Mercury's tenuous exosphere is locked in a constant dance with these energetic particles and the magnetic fields that guide their movements. The solar wind, a plasma composed primarily of protons, electrons, and alpha particles, carries with it a magnetic field frozen into the plasma and dragged along with it as it flows outward from the Sun. This magnetic field, known as the interplanetary magnetic field, interacts with Mercury's own magnetic field, creating a complex and dynamic region of space known as the magnetosphere. Mercury's magnetosphere, while significantly smaller and weaker than Earth's, acts as a protective bubble, deflecting most of the solar wind around the planet and shielding its surface from the full brunt of its onslaught. The interaction between the solar wind and Mercury's magnetic field creates a boundary known as the magnetopause, where the pressure of the solar wind is balanced by the pressure of Mercury's magnetic field. However, Mercury's magnetosphere is not impenetrable. Its weak magnetic field and close proximity to the sun mean that the solar wind can sometimes penetrate the magnetosphere, particularly during periods of heightened solar activity, such as solar flares or coronal mass ejections. These intrusions of energetic particles can have a significant impact on Mercury's exosphere, stripping away atoms and molecules, altering its composition, and even triggering auroral displays similar to the northern and southern lights on Earth. In the grand tapestry of our solar system, where gas giants swirl with majestic grandeur and icy moons harbor hidden oceans, Mercury might seem at first glance like an unlikely candidate for our attention. Its surface, a desolate landscape of craters and ancient lava flows baked by the relentless heat of the sun, might appear to offer little in the way of scientific intrigue or the promise of new discoveries. Yet, beneath this seemingly barren exterior lies a world of surprising complexity and enduring allure, a world that continues to beckon us with the promise of unraveling some of the most fundamental mysteries of our solar system's formation and evolution. Mercury's close proximity to the sun, while presenting significant technological challenges for space exploration, also makes it a unique and invaluable laboratory for studying the processes that have shaped our planetary neighborhood. As the innermost planet in our solar system, Mercury has borne witness to the full fury of the sun's evolution, its surface a record of the intense radiation, solar wind, and micrometeoroid bombardment that have characterized the inner solar system for billions of years. Furthermore, Mercury's unusual characteristics, from its massive iron core and 3-2 spin-orbit resonance to its highly eccentric orbit and weak but persistent magnetic field, offer tantalizing clues about the processes that govern planetary formation, internal structure, and the interaction between planets and their host stars. Each new discovery about Mercury, each piece of data gathered, brings us closer to understanding not only this enigmatic world, but also the broader principles that govern the evolution of planetary systems throughout the cosmos. From Mariner 10's flybys in the 1970s to Messenger's orbital mission ending in 2015, each mission revealed Mercury's secrets, transforming our understanding of this enigmatic world. Messenger mapped Mercury's surface, studied its magnetic field, and discovered water ice in shadowed craters, reshaping our knowledge of the inner solar system. The exploration of Mercury is far from over. Future missions promise to revolutionize our understanding of Mercury. Bepi-Colombo, a joint mission, will study Mercury in unprecedented detail. Bepi-Colombo will address fundamental questions about Mercury. Scientists envision even more ambitious missions, including landers. These landers could reveal clues about Mercury's early history. As we explore Mercury, we uncover secrets revealing fundamental truths about the universe. Mercury's unique characteristics offer insights into planetary systems and their evolution. Its extreme environment helps us understand exoplanets and their challenges. Studying Mercury refines our models of planetary dynamics and geophysics. It deepens our appreciation for the complex nature of our universe. Thank you for watching. Please hit the like and subscribe button to get notified of our future videos on cosmic wonders. Keep asking questions and stay curious. The universe is full of mysteries waiting to be unraveled. Until next time, keep looking up.